All right. Lovely weather today. Good morning. How's everyone doing? Great. Good to hear it. Nice to see all of you. We have a big one today. I'm hoping we make it to regression. So we have to finish up our discussion on hypothesis testing. We'll do a couple examples. We ended last class really just getting started with the idea of hypothesis testing. So what we're doing today is refreshing our memory on what we were starting to do last time, and then doing some examples, and then we are getting into regression, which makes me very excited. This is the workhorse model of essentially everything we do in economics. At least involves some component of regression of some kind. So regression is the big model. In practice, well, we'll talk about this in a little bit. We don't actually do like a ton of like hypothesis testing in the way that we do it in these next couple examples. But the way we think about hypothesis testing applies to like almost perfectly directly to linear regression. So we're building up this idea of what a hypothesis is, how we test it using the central limit theorem and the normal distribution, and then we build models and we test those models. So this is pretty exciting stuff. I ran about 1,000 of these in my, that's an exaggeration. I ran a bunch of these in my dissertation, and you're going to run a couple of these in your final project. Thanks to everyone who's sent me your groups. Good to hear from you all. I hope it's exciting thinking about working on a project of this type and working with someone interesting in the class. So make sure you're talking about project ideas, maybe doing some brainstorming. If you're not using generative AI, you are leaving grade on the table. So make sure you're using it just to sort of brainstorm ideas, figure out something that might be interesting and feasible for you, and maybe some data sources. So feel free to get started like tonight as you like. Okay, so let's pick up where we left off 2 classes. No, just kidding. Last time. All right. Tough crowd today. Maybe we've, or maybe it's just a terrible joke. Okay. We never leave off where we left off 2 classes ago. We only ever pick up where we left off last time. It's the rule. So we talked about, going back a couple of slides, we have the population mean. We have this interval estimate around the population mean, which gives us our confidence intervals. And we have different levels of confidence depending on the size of the interval. The larger the confidence interval, the more confidence we have that the true parameter, when we sample a bunch of times, will be on the inside of that interval. So through repeated sampling, are we confident that the population parameter will be on the inside of the interval? So we ran through an example last time. We're trying to evaluate a candidate population parameter. So we don't know what the population parameter is, but we're wondering, is it something specific? And so we have this test drive where we have 10 Fords, and we have the sample mean, which is 31.8. We have the sample variance, which is 2. So the sample standard deviation is square root of 2. And then we're wondering, is mu going to be greater than 30? And so we can run through our little example and sort of test these things. So the first thing we do is we construct the confidence interval, which we did in the previous example. So we have an upper and lower bound on what the 95% confidence interval looks like, which is 2 standard deviations above and below the sample mean. So we multiply 2, because this is a 95% confidence interval. We know this is 2 using the empirical rule. Just 95% gives us 2 standard deviations away from the mean. So this tells us, how confident we would be that the true parameter lives inside that interval on repeated samples. And we said, our requirement was that we wanted the average to be above 30. So is the true parameter above 30? And so we can see that the confidence interval on both ends lives above the requirement. So it's no more than 2 away. All right, and I gave you this little caveat. The language we use here is about repeated sampling. We're not saying something specific about. So we know the true parameter. We don't know the true parameter, but we know the sample mean x bar. The true parameter has no noise to it. It's not random. So we have 2 things that are not random. So we can't really say something about the randomness between the 2. What we can say is that on repeated samples, the true parameter will live on the inside of the 95% confident interval 95% of the time, which is exactly what it's doing. So this is the sort of shorthand terminology for that idea. And then, so the sort of summary here, we have our information. We calculate the standard deviation for the sample mean, and then we plug in the sample standard deviation, and that gives us the standard deviation of the sample mean. And all we're doing essentially is using there's a lot of different ways of thinking about these things, but it all essentially boils down to this one idea, which is we want to test the difference between our check, the candidate mu, and the x bar. So we look at the absolute difference between those 2 things and then check it against the standard deviation of the sample mean. And then we check it against different levels of confidence. So here we have the absolute difference between our candidate 30 and our x bar, which we calculated from the data to be 31.8. So that difference is 1.8. And then all we're going to do is check this against this sigma x bar, which we can get from the data. And this 2 just comes from how confident we would wish to be. So how big is our confidence interval? So this is sort of our confident, our critical value approach, where we're checking the actual deviation between the 2 things against the deviation, sort of the width of the confidence interval, either side of the confidence interval. And here we are okay. 2 times 0.447 is just below 1. So the difference between 30, our candidate, and x bar is greater than the 2 sigmas. So here we're saying we can be very confident that the true parameter is greater than 30. And so we walked through some of the picture for why that would be here. So this thing is very far away from this. And all we're saying is 2 sigmas is much smaller than this blue interval. So the red one, the 2 sigmas, is much smaller than the big one. And that's essentially all we're doing with hypothesis testing. It all boils down to like basically this picture. Like how far away are things? Sigmas, confidence, levels of confidence, and then the candidate against the sample mean. Yeah, Marcus.
Why don't you take the absolute value?
Yeah, because we're essentially testing 2 different directions. So it could be that we wanted something that was greater than the mean. So like, let's say we wanted to make sure, the mileage wasn't too good. It would be a funny thing to test, but we could. And so if we were testing like 34, like let's say we wanted all the Fords to be less than 34 miles per gallon or being paid off by the big oil companies. In that case, we would want, we'd still be checking the absolute difference, but it'd sort of be like in the other direction. If we didn't use the absolute values, we get a negative or a positive, and that's not. We're really just checking the distance between the 2 things. Yeah, the 2 values. Yeah, good. What else? Questions are good things. I hope you get the intuition for what we're doing, and I hope you get the skills to do this by hand, but also some of the Python skills, which we're going to start sort of leveling up. So these are the three things I hope for you. Okay, so nice. So this was example 2. I did this in Python, if you want to take a look. So in our example, we had a sample size of 10. So our sample size was 10. Our X bar was 31.8. So our X bar was 31.8. And then our standard deviation of the sample was square root of 2. So once we're adjusting for the sample size, we use the S central limit theorem, and then we're plugging this into an absolute difference. So we check our hypothesis, which we'll talk about more, the terminology we use here. But the essentially like the candidate that we're checking is 30. So we wonder about 30. We take the absolute difference, so the absolute value of the difference. So this is just NumPy is just our numbers package in Python, and from that we're importing NumPy as MP. We're just sort of renaming it. It's like you can call me Tay. That's all we're doing here. It's like NumPy, but we're going to call it MP. My name's Taylor, but you can call me Tay. That's what this is doing. Don't call me Tay, actually. I had a friend in college who called me Little Tay, which was funny because I was way taller than her. So this is the absolute value of the difference. So what Marcus was wondering about, we are taking the difference between these 2 things, and then we check this thing against the 2 standard deviations. So we have this thing, which is coming from the variation in the data itself. But then because we're considering, we can only start working with the central limit theorem and the normal distribution when we take when we're looking at the distribution of the sample mean itself. So we have to, for all of the central limit theorems to start applying, we actually have to consider S divided by the square root of N. That's where the normal distribution starts applying. So so we divide this thing by the square root of 10, which gives us this thing. If we printed it out, this would be S CLT we print this out. So that gives us the standard deviation of the sample mean. So that's this thing. And then we're just multiplying it by 2 to check if it's 2 standard deviations away, or like what the value is that's 2 standard deviations away from X bar. So how large is the one sort of side of the confidence interval? If we wanted to check at a 99.7% level of confidence, we could multiply this by 3. And again, we'd still be 99.7% confident that we are that the average is the miles per gallon is greater than 30, because our difference, the difference between our candidate and the X bar, is greater than 3 times that sigma X bar. 3 times the sigma X bar is this thing. Just printed it out here. 3 times sigma X bar. And that's smaller than our 1.8. Okay. Any questions about this? So we're very confident that the average is above 30. That's what we're trying to say. All right, nice. And you might have seen I posted the notebook I'm working with. You can actually just, I think you can view it live. If you just click on this, it'll take you to the collab. So you can just play around with this. I think you can't edit it. At least I hope you can't. Please don't edit it if you can. But you can take a look at it, play around with these things, use it with your homework, etc. And that's just right here. And then after class, I'll post the notes, the slides for this one. All right. So nice. We also talked about the sample proportion. Essentially, everything we've just done with sample means applies when we're considering proportions. The distribution of sort of binomial variables is a distribution itself. And so everything we've done with the central limit theorem applies when we're considering proportions. So what's the proportion of everyone living in the United States who likes the color blue versus the color yellow? That's a proportion. It's going to be some fraction. So some number between 0 and 1 will prefer the color yellow over blue. And that's a distribution in itself. So I've said this once already, that everything about the central limit theorem and our ideas of normality apply with proportions in exactly the same way as they do with any other type of mean. So it works in the same way that the distribution of the sample mean of heights of everyone in the United States works in exactly the same way. As the sample size gets larger, we approach a normal distribution with a particular shape to it. And it's centered on the true mean. The only difference, though, is that the standard deviation looks like this. It has a very particular form. So instead of asking the data to give you the mean and then also the standard deviation of the sample, because of the binomial distribution, you just need that one number, and that will give you both things. So it's actually a little bit simpler, but the core ideas apply in exactly the same way as they've done in the past. P hat follows a normal distribution centered on the truth, or centered on the truth as represented by this thing. It follows a normal distribution with a spread where we have the variance as P times 1 minus P over N. Okay, and so empirical rule applies in exactly the same way because, again, it's simply from the normal distribution, we know that this thing is or from the central limit theorem, we know this thing follows a normal distribution with all the characteristics we're familiar with. Okay, so estimating a population proportion, we have a point estimate, just like we've done, and we have a confidence interval. So again, putting a confidence interval around a population proportion estimate, it happens in exactly the same way, plus or minus whatever number of standard deviations we're considering, multiply that by the sample standard deviation, sigma p hat. Okay, and then it just, upper and lower bounds critical value times the sigma p hat, and that gives us the interval. Okay, and this was my terrible slide that I forgot to fix, where I gave you all the boxes beforehand. We just went through and constructed all of these particular numbers. So this was first, we needed, if we're going to ask the question about the 99% confidence interval of the proportion, we have to construct the standard deviation of p hat. So the main question was, are celebrities on social media influencing people to buy things? Which is not a very statistically well-framed question yet. So we started this off by looking at the sigma p hat. We know what the p hat is, so we can construct the sigma p hat. This is the thing that's different. We don't need two numbers, we just need the one. So we construct the sigma p hat. We essentially plug in the numbers into the binomial, and that gives us the sigma p hat. Then to construct the confidence interval around p hat at a 95% confidence level, we multiply 2 times the sigma p hat, which, remember, often people forget to divide this number by the square root of n. Make sure when we're doing anything with confidence intervals, we need to be adjusting for the sample size. That's a common mistake. So make sure we're adjusting for the sample size by dividing this thing by the square root of n. So we get the 0.014. We multiply by 2 so it's like upper and lower bound 2 standard deviations, because we're looking at the 95% confidence interval. And remember, this is this is rounding. This is like when we plug these things into Python, we get slightly different numbers because the empirical rule is an approximation. So this 2 is an approximation, but it's okay to use. It's like close enough. People use them in papers. I never have, but it's okay if you do. And then here we have, we're just multiplying this thing by 2. So this is upper and lower bound 2 standard deviations away from the population proportion. And that we just run that through a calculator and it gives us the numbers. Okay, so let's do this with some Python. So this was example 3. So essentially what we're doing, we have our sample size of 1,000. We have our population proportion of 26, 0.26. And so we have that here. We know what the standard deviation of the sample is. It's just p hat times 1 minus p hat. So that gives us our S. Then we have this SCLT, or you could call this like SP hat if you like, to be more consistent with the slides. And then what we're trying to do is just find the confidence interval for this sample. And like what we've done before, we say, okay, we're going to unwrap our package. It's almost holiday season. You may be getting presents. All we're doing is unwrapping the package. There are more than one present in the package. We're pulling one of them out and calling it norm. Short for Normand. Yeah, short for normal. Sorry. They don't get better. They never do. So then what we're doing is we're trying to find the confidence interval around our p hat. So the way we do this is we center the distribution, the confidence interval on p hat. So we use the parameter lock, and we say that Python should assign p hat to the center of the confidence interval by, this is like short for location. And then the scaling is just sort of the distribution of the sort of the width of the distribution. So the standard deviation. And then this just tells us the level of confidence we would wish. And then all we do is we just print this out. So we'll just run this, and that gives us these numbers here. So we just run this through Python, and it's giving us something very close to what we've done using the empirical rule. Although this is rounded and it's slightly different. Okay, so I actually want to pause here and make sure that you're comfortable running these things. How many of you have run something like example 2 or example 3 already? Okay, so I want to make sure that everyone in the room is comfortable running these Python commands. How many of you have already been started with Colab? Oh boy. So let's pause here and get started with Colab. I'm running through examples. I was under the assumption, incorrectly, I guess, that you all were feeling sort of comfortable with these things. With your computers, we're actually going to get started using Colab today. I want to make sure you're comfortable doing these things instead of just watching me run through them on the screen. Okay, so this is some work for you right now. The first thing is you should be able to, I think, essentially just go to the part 3 page and click on the notebook, and it will open up a new tab for you with the notebook loaded. Let's get started doing that. Okay, so Tony, you're in?
Yeah,
Okay, and are you able to edit the file?
Yeah.
Okay. So I believe that must open it locally for you. Okay, so what's nice about Google Colab is you don't have to install Python locally on your computer. There are, 15 years ago, this wasn't available. But now that we have nice cloud services, you can run Python in your web browser. What this is doing is it's essentially using Google Docs. So it's creating for you a Google Doc, and then you're able to edit the Google Doc. It's just that the Google Doc itself is a Python program. So one thing I want to do, we're going to take example 3, and we're going to turn this into a 99% confidence interval. And you're going to tell me what this number is. So I'm not going to show it on the screen. We're going to take like a couple of minutes here, and I want you to run this command in Python on your computer and tell me what the 99% confidence interval for example 3, what that is. Okay. Yeah, Devin. Maybe we should back up. Colab is Python. It's a Python notebook it's sort of built into Google Drive. You're running Python in the Colab. It's like, Colab is like the service that Google provides. Notebooks are a document, and then Python is the language. Okay. Yeah. Okay, so once you're getting started, once you're finished, check with your neighbor about what the numbers are, and then we're going to check back together. And if you run into trouble, don't hesitate to ask for help. Getting started with Python is not trivial. It's an important skill, just to at least have some access and some practice with these things. So we're looking for the 99% confidence interval around this sample mean. Okay, how many of you have finished? How many of you are still working? Some of you didn't raise your hand. If you didn't raise your hand, I'm also assuming you weren't laughing at my jokes, which I will take personally. Okay, so what you'll have now is, how many of you use Google Drive regularly? Okay, so if you use Google Drive regularly, essentially no matter whether you use it regularly or not, you should now have a new file in your Google Drive with these examples that I've run through in class. If you don't, there's maybe a way to go up to, you can locate this in Drive. So for me, this is in ECON 0100, 0150. And this is just what it looks like. It's just a file in my Drive, and it has some classwork that we've done. And then if you were to click on this, it would just open up a Colab notebook, which allows you to run Python. So that's essentially all it's doing. And each one of these cells can be run separately, like we've talked about before. You can just hit, for me on a Mac, it's Command Enter, and it runs the cell. But you could also just click Run, and it will run the thing. So no matter how you use it, you need to be using these things. We're sort of getting started using Python with these simple examples, but we're about to run regressions using Python. So this is a little bit harder to do in Excel than it is in Python. Python actually makes running regressions pretty straightforward, which is the reason we're using that and not Excel. Okay. Any questions? So stick around after class if you do have questions. But yes, you can always just access the notebook here. As we go through these things, I'll keep a sort of a running update on the notebook, and then notebooks as we go through. Okay, so these are the numbers I get for the 99% confidence interval. Anyone else gets? Raise your hand if you got this number, these numbers. Yeah, there we go. Nice. Raise your hand if you didn't get these numbers. You got a different number?
I didn't get anything. I got error.
Okay, let's chat after class then. All right, so nice. Let's keep rolling. So this is the confidence interval for the p-hat. And then we can check a bunch of candidates. What the confidence interval allows us to do is, build some level of confidence, which tells us on repeated samples, how often will the true parameter live on the confidence interval of these repeated samples. And so one question we could ask, like we did last time, is p greater than 0.25? And the answer here is we don't know. We can't say for certain that the truth is greater than 0.25, even though our sample proportion is greater than 0.25. And the reason is that some of the confidence interval lives below our candidate. So 0.25 lives on the confidence interval, which tells us that we can't say for certain on which side of 0.25 the truth is. Okay, so this was our idea from last time. And then we asked a different question, which was, is is the true parameter p less than 0.3? And so we could plot this out here, and we can see the entire confidence interval is below 0.3, which means we're at least 95% confident that the truth is below 0.3. If we were to repeatedly sample 95% of the time, the confidence interval would not contain the truth. Okay, so the answer is yes, because the 95% confidence interval is below the hypothesis. So I've used the word hypothesis. We haven't really introduced this term yet, but that was essentially what we were doing. We're introducing a candidate, and we were going to check it using the confidence intervals that we've just developed. So we're going to talk a bit about what a hypothesis is. We hit this at the very end of class last time. Essentially, a hypothesis is a claim about the population parameter. We can't see it, but we can say something about it because we have the central limit theorem and our confidence intervals. So two examples. One that we talked about last time was the mean cell phone bill for the city of Pittsburgh being $42, which is much higher than what I pay. Hopefully you too. Starting to sound like Ryan Reynolds. Yeah, I heard someone laugh. Okay, all right. I'll take whatever I can get. Population proportion, we could do a hypothesis, a claim about the population proportion again. So population of the proportion of adults in the city with cell phones is 0.68, which feels pretty low, but that would be a claim we could check. So we essentially split our hypothesis testing into kind of two parts. One, we have a null hypothesis, which is the claim we're trying to reject. And then what we do is we try to reject the null. So we set up the null hypothesis, which in this example, the mean diameter of a manufactured bolt being 30 millimeters, the null hypothesis is that it's 30 millimeters. And then what we do is we take our confidence intervals into that assertion, that claim, and then we try to reject it. As we'll talk about at the end, we can never, the opposite approach doesn't work. We don't ever accept hypotheses. We just fail to reject. So this is going to be essentially our approach. Here's some examples. I don't always love these, but we're using the null hypothesis as like sort of our baseline, something that we take as true until we can reject it. So like in this country, you're innocent until proven guilty. A new product is no different than the old one until we prove that it's better. So this is how we do medical trials. You have to prove something is more effective than the thing that came before it. So the average salary after graduation is $46,000 until proven different. And then the average wealth is at least $100,000 until you prove it's like less than that or greater than that if you wish. So we're taking a claim and then we're trying to prove something different. We're trying to show that the claim is not true, which is essentially all we can do with hypothesis testing. It's the sort of general approach. Okay, and the reason we can't accept things is because what a confidence interval sort of allows us to do is reject like tails, like the distance away. There's a bit of philosophy. I remember spending summers at my work study job in college, like debating the philosophy of this stuff. But this is like the standard approach. We can chat more about how to think about these things more generally if you like. So there's some nice summers. Okay, so here are some null and alternative hypotheses examples. So a null hypothesis, essentially we're checking whether the mu, the truth, is equal to some check. So if the null hypothesis is H naught, we're checking whether the truth is equal to that thing. And the alternative hypothesis, the if we reject the truth, what would be true instead? Would be this thing. So it's essentially just, is the truth equal to mu naught, or is it not that? Would be the alternative hypothesis. Sometimes we call this H1 as the alternative. Sometimes we call this HA as the alternative hypothesis. Just both standard notations. We could also do these like one-tail tests where we check whether the truth is equal to or above. So is the truth no less than mu zero in green? And in that case, the alternative hypothesis would be that the truth would be below mu zero. So we're essentially like, if we can say for certain that the truth is not above mu zero, then that would mean the truth must be below mu zero. So if we can reject one of them, that means we confirm the other one. Although we have to be a little careful about that language. And then again, we could do the other direction in blue. Null hypothesis essentially always involves inequality. So all three of these null hypotheses involve inequality. And then, like I've said before, the core idea is that we reject the null, which then tells us something about where the truth is not. Okay, so how do we do this in practice? So let's use an example here. We have an M&M plant manager looking at their production lines, and then for the company specification, we need a certain number of green M&Ms. And what we're saying is it has to be on average 4. So then what we're doing is checking the population mean. We're checking whether the population mean is different from 4. So if it's not different from 4, then we don't do anything to the production line. But if it is different than 4, then we would have to like shut down the plant, update the manufacturing line, and then restart the plant. So this is sort of one of the types of applications we could use. So we'll just run through a bit of a little example here. So the check is that the population mean is 4. That's our null hypothesis. It's like in the specification documents for how many green M&Ms should be in a bag. So we want to check whether it's true or not. And then we try to reject it. If we reject it, that tells us something about the alternative hypothesis. But the alternative hypothesis, we leave these very general, right? Like saying it's not equal to 4 doesn't tell us what it actually is. It's just saying it's not equal to 4. So how do we test the null hypothesis? Well, like we've done with confidence intervals, if you're feeling like we've already sort of done this before, it's because we have, just using slightly different terminology. We randomly sample the bags. We calculate the number of green M&Ms there are in each bag, which gives us our X bar. And then we compare it to what we would expect to see if the null hypothesis were true. So we're going to get into a bit of technicalities, but I want you to be thinking about that core idea of the deviation between our candidate and our X bar against the standard deviations and our critical values. It's really just, we're checking 2 numbers. Okay. So how does this work in practice? So let's say we have an X bar of 2.8, which is a lot lower than 4. And we're going to say it's significantly lower than 4, whatever our confidence interval is. If the null hypothesis were true, the probability that we would get a value that much lower than the sample mean would be very small, which is the core idea in the central limit theorem. If we're randomly sampling and the distribution itself is centered on 4, to get a very small number would happen very infrequently, right? I wish I had a picture of this on the slide. But if, we will draw pictures like this on the slides in a bit, but if it's centered on 4, it's very unlikely that we haven't like specified the significance or the standard deviations, but it's very unlikely that we get an X bar of 2.8, which is we're saying is significantly different from 4. So all we're saying is, if we were to center the distribution on 4, 2.8 does not happen very often. And so this tells us some level of significance that the alternative, that the null hypothesis is true. And it turns out it's very, very unlikely. So the language we use is that we reject the null hypothesis. Getting this mean is very unlikely if the population were actually 4. So we conclude that, with our level of confidence, that the truth is not 4. Okay, so this is sort of the way we think about these things. The picture I wish I had on the last slide was something like this, where we have our confidence interval around X bar, and then we have our check, which is far away from the truth. And the other way to think about it, remember, we've been switching back and forth as we like, whichever one is most useful, between centering the distribution on the candidate, the hypothesis, or centering it on the X bar. Either way we do it, it's mathematically identical. Remember that picture from last class and the class before. So one way of thinking about hypothesis testing is we center the distribution on the hypothesis itself, and then how likely is our X bar, given that the distribution is centered on on H naught. And it turns out if X bar is outside of our confidence intervals, then we can reject the null hypothesis with whatever confidence we're using to construct the confidence interval. So in this case, using 2 standard deviations would be 95% confident. Okay, so a bunch of like technical stuff, some pictures I want to run through. If this is more complicated, like this doesn't offer like a whole lot of extra intuition for me sometimes. Some people like to see these things. But if you're all set with this, with the intuition, with the picture I just showed you, with this one, stick to this. I'm going to walk you through some of the ideas with a general example. So with our normal distribution centered on mu, we call these areas in the tails rejection regions, which is essentially just, we want 95%, if we're using 95% confidence, we want 95% of the distribution to fall within 2 standard deviations of the mean. And then the rejection regions are just all of the other probability pushed to the tails. And because this is a 95% confidence level, we have 5% that needs to take up both of the tails. Because it's a normal distribution, it's symmetric. So each of the 2 tails has on its own 2.5%. And we call these the rejection regions. So we're centering the distribution on our hypothesis, and then we're looking at the 2 regions. So we have 5% is the size of the 2 red regions. What we're saying is that it's this 5% is the probability that we observe X to be in the tails, in these rejection regions, given that the hypothesis is true. Which, the way I've been saying this, in the class is we're centering the distribution, the normal distribution, on the truth, and then we're finding the how far away the tails would be. So, given that the truth is true, how far away are the critical regions? So it gives us the probability in those regions. And we can say this a couple of different ways, but you can start to see the conditional probability notation show up, like what we were doing in part 2. So we have the probability of observing X bar in red, given that the null hypothesis is true. And that's equal to 5%. So we're conditioning our probabilities on the null hypothesis being true. So just mathematically and sort of notationally, this is some of the connection to the ideas of probability theory that have led us into statistics. So this is saying, what's the probability that X is too extreme to occur, given that the null hypothesis is true? And then we're saying 5% is the probability that we find evidence to reject the null hypothesis, given that the null hypothesis is true. So we're saying the 5% represents how likely it could be that we're wrong. That's what these critical regions tell us. So the smaller the critical regions, the less likely we're wrong. Okay, so that's part of why we use, why we like smaller numbers for the rejection regions, and why when we want to be absolutely certain, we use more sigmas. So 95 uses 2, 99.7 uses 3. If you're doing any like particle physics, you use 5 or more. Yeah, Devin.
I guess I'm just a little confused with the M&M example. Like, what exactly is the relationship between the 4 and the 2? Like, this I get, but like,
Yeah.
in that specific example, like, what is the relationship between the 2? And what does that mean that, like, if it rejects it, so does that mean it's not in the tables?
To reject it, we're saying that if we were to center the distribution on 4, it would be very unlikely for us to see the 2.8. So that tells us that it's very unlikely, sort of the converse is very unlikely, that the truth is actually centered on 4, that the truth is 4. Does that work?
I just don't really understand like what the 2.8 is, because that's not like the standard deviations is really still. Is it the percent, like the 5% in the next region? Or in the
so it's related to the 5%, if I'm understanding your question correctly. The 2.8 is the sample mean. So we sampled a bunch of bags, and that came out to be 2.8. So we're seeing a 2.8 in our sample, and then we're asking, if the truth were actually 4, how likely are we to see a 2.8?
Okay, gotcha.
So in some sense, we're sort of flipping some of the logic of confidence intervals. We're putting the confidence interval around our guess, or the thing we're trying to check, and then we're seeing how far away 2.8 is from that thing, given the distribution. Does that work?
Yeah, thank you.
Okay. All right. Any other questions here? Questions are a very good thing. Sometimes I keep track on the board. Maybe we'll do that next class. So this was our sort of general example, but we can even go more general than that. No matter what the level of confidence is that we're interested in, we generally use, at least in economics, we use alphas of 5%. Sometimes we use 1%. Sometimes we use 10%. Whatever the alpha is, we can find the rejection regions using alpha over 2. So this is just, the normal distribution is symmetric, and so we need to check both tails. It's just alpha over 2. And essentially what this tells us is the probability that we're wrong. So if we want to be certain that we're not wrong, we make alpha smaller. How likely are you going to be that you're wrong? Well, we want that to be small. This is what we call a type 1 error. The probability that you reject the null hypothesis, even though the null hypothesis is true. Reject the null given that the null is true. And that tells us the significance level. So alpha, we interpret this as the probability of making a type 1 error. How likely is it that you're saying something isn't true when it actually is? Okay, and we greatly dislike this. We can also talk about the probability that you sort of the opposite is true, which is the area on the inside of the two sigmas. This is our sort of confidence level, and this is we like these things to be large. So it's the opposite of the type 1 error. Okay, that's a lot of stuff. The last slide here is with the language. So one thing we can say is if X bar falls in the rejection region, we reject the null hypothesis with whatever the significance level is as a percentage. So if, for example, if our standard one is this second one, which is alpha is 0.05, so we can say that we reject the null hypothesis with 95% confidence. That's sort of our standard terminology, which is sort of shorthand for this idea of repeated sampling and the truth living on the intervals some percentage of the time. And we get that from the central limit theorem. And then we say if it falls outside the region, we can't reject at this level of confidence. But we don't say that we confirm it. Okay. So yeah, I feel like we've spent a lot of time talking about the intuition. I'll just say it one more time, just so we get this said one more time. But gosh, I really want to get to linear regression. So if X is essentially close to our hypothesis, then close being relative to the standard deviations, then we do not reject the null hypothesis. So if X bar is close to mu on the distribution, then we can't reject it. If it's far away, then we can reject it. And the way I conceptualize these things, because we can sort of switch the distribution back and forth between centered on the X bar and centered on the guess we're making, the way I think about it is we construct the two sigmas away from, we construct the two sigmas, and then we compare that difference to the difference between our X bar and our check, whatever it is. And if it's closer, then we fail to reject. And if it's further, then we reject. Okay. Questions? So we have two approaches. The first approach is with the critical values. And the idea here is we're setting H naught, and then we're picking our significance levels. And we have a known sample size. And the idea is that we use alpha to set the critical values and the rejection regions. Once we do that, we can compute the test statistic. And then once we have the test statistic Z, then we compare that to whatever critical region we're considering. So we've done a lot of these types of things, like the sort of general approach will feel very familiar to you from the homework. So once we have the Z value, then we compute the test that's the test statistic. We compare that to the critical region, which is essentially those sort of absolute differences. And then we compare them to the standard deviations times our critical values. And we can reject if they're very different, and we can't reject if they're not very different. So this is the general approach. We'll do one example in two ways, and then if we have time, I want to introduce linear regression. All right, so I've been watching a lot of sports recently. Exciting city to live in at the moment. Pro Bowl happens in Hawaii, and the Hawaii Tourism Authority is trying to estimate how long people stay. So in ancient history, they surveyed a bunch of visitors, and they came out with an estimate. So the X bar was 9.1 days, and they had a standard deviation of 5.7. So we have the X bar in green, and we have our null hypothesis in blue, which is that the average length of stay is 10 days, 0.1. Very precise. The alternative hypothesis, all we're going to claim is that the alternative is not this. Okay, so then we have the number of observations is 260. The standard deviation is 5.7. So can we reject their claim with 95% confidence? That's the thing we're about to walk through. Okay, so what's the approach we take here? Someone walk me through some of the logic of this. Like, just given this information, where do we start? What's maybe a first step? You've done similar things on your homework. And you will do similar things on the homework that's posted. So how might we approach this problem? Yeah, we have linear regression to get to. Help me out. Should we do it together? Or should we do it on our own?
Let's do it together.
Okay. Let's do it together. So when I see this type of question, I immediately go to what's the distribution? What's the sort of variability of our sample? And the way we know, the way we can get the variability of the sample, the distribution of the sample mean, we look for the standard deviation in the data, which is 5.7 days. And then we also have the number of observations. So these two things together will give us the sigma X bar. So that's where we're going to start, which will allow us to set up the test statistic. Okay, so we have our X bar, we have our S. What we're going to do is construct the sigma X bar. So we don't know sigma, but we do know S. And because the sample size is very large, we can substitute these things in. So we're going to substitute S in for sigma. So we have 5.7 divided by the square root of the sample size, our n. So this comes out to be this number. You can just, I'm walking through these steps without actually plugging this into a calculator because I've already done it. But you can check these numbers with your calculator. This is the place to start. Okay, so once we have our sigma x bar, we know the variability of the sample mean. And if we're thinking about a 95% confidence interval, that's telling us that we want to check whether the two numbers, the x bar and the hypothesis, are 2 sigmas away from each other. So we know what sigma is, and we can find what 2 sigma is. Another way of sort of writing this out is to compute the z value, which is the critical value approach. But in the back of your mind, you're always thinking about 2 sigmas. Is the difference between mu and x bar 2 sigmas away from each other, which is essentially what we're doing here. So we have x bar minus our mu. We have x bar minus our mu divided by our sigma. So we have x bar, which is 9.1, subtracted 10.1, which is the thing we're trying to check, which is our null hypothesis. So we plug in our null hypothesis in for mu, and then we divide it by our sigma x bar, which is calculated here. So that gives us this number, which is a way of saying how far away relative to the distribution, like how many sigmas away are these two numbers? How many sigmas is x bar away from our hypothesis? This tells us that they're 2.86 sigmas away from each other. So the absolute value, as Marcus was telling us earlier, gives us this number, 2.86, which is greater than our critical value. We would, at a 95% confidence level, we would wish them to be, if we're going to reject, we need that z-score in absolute value to be more than 2. So because we know they're 2.86 sigmas away from each other, this tells us that we're 95 or more % confident that the two numbers are not the same. People spend less than 10.1 days in Hawaii for the Pro Bowl. Okay, any questions here? You'll get the slides. So this one, the alpha, or the 2?
The 2.
Yeah, so that comes from our 1, 2, 3 rule, or the empirical rule. Exactly.
Oh, okay.
Yeah. How many sigmas away is 95?
Okay.
Yeah, related to. Okay. Any other questions? All right. So that's nice. We can do the same thing for our 99.7% level of confidence, or 3 sigmas. So we can plug in the same hypothesis. All we're doing is changing the level of confidence. Our sigma x bar doesn't change. Our x bar doesn't change, and our s doesn't change. So our z value stays the same, even if we're looking at a different level of confidence. The only thing that changes is our comparison. We're comparing the absolute value of our z-score to a different critical value. Because we're considering 99.7%, we now consider 3 standard deviations away. So essentially all we're doing is looking, is the x bar 3 standard deviations away from our guess, from our hypothesis? And the answer here is it's not more than 3 standard deviations away. So we can't reject the null hypothesis at this level of confidence. Okay, any questions here? I think you need some practice with this stuff. There are problems very similar to this on the homework. I want you to take a look at those things. Use this as a guide. Go when I post the slides after class, use this slide and try to start here without any without any clues. Just use this question without seeing the answers. Part of what gets people tripped up on these things is just getting started. So I want you to look at this thing, feel stuck for a little bit, and then figure out ways to get unstuck. Figure out what the process is and how to move forward through that. Okay. You're going to be asked to do a lot of these things, not just by hand, but also with Python on the homework. Okay, and I've given you lots of examples of how to do this in Python on the part 3 page. Okay, so just some wrap up here. So we were able to reject H0 at a certain confidence level. We can reject it at any confidence level below that, right? So it's like we had this z-score, which didn't change based on what level of confidence we were looking at. It's just the level of confidence would change in comparison to the z-score. So when we were wanting to be very confident, we had a critical value of 3. When we were wanting to be less confident, we had a lower critical value. But if we wanted to be even less confident, we could reject that as well. So the like 97% confidence level, we could reject that as well. Okay, so that's one of our conclusions, but the opposite doesn't hold. So as we went from 95 to 99, we could no longer reject it. And that's because the more confident we want to be, the wider the confidence intervals are. Okay, so I just answered that last question and showed it in a graph because as we wish to become more confident, we have to extend our confidence intervals. Okay, so this is some useful facts for you to hold on to in the slides. I'm not going to talk through them. There's another approach to hypothesis testing, which we'll pick up next time. But before we go, I want to show you a couple of pictures. About 2 minutes. I'm going to take all of our time. So what we're going to start talking through next class is what we call the general linear model, which is a very broad model. How many of you have heard of a t-test? How many of you have heard of ANOVA, analysis of variance? How many of you have heard of regression? These are all variations on the same model. They're all variations on the general linear model. So what we're going to do with essentially the rest of the semester is talk about ways of understanding and using the general linear model, when to apply it, and how to apply it in different contexts. We're also going to talk about how to interpret the results of our models. In economics, we spend a lot of time thinking about relationships between different types of things, like one's foot size and how fast your marathon time is, for example. It's not really an economics question, but those kinds of things, relationships between variables. We like in economics to think about causality. Does your foot size increase or decrease your marathon time? What we're going to do in regression is build lots of models of correlation. We want to make claims about causality, which is a much more difficult problem. So what we're going to do in this class, in addition to talking about or correlation, is we're going to think at least a little bit about how we can model causality. We're not going to be able to solve the problems of causality. We're just going to think about how we can set up causal relationships in models. Okay, I don't want to be rude and keep you over time. Next time, after we walk through another example, we're going to talk about relationships between variables, which should get you thinking about part one, what we did with data visualization at the beginning of the semester. All right, have a nice weekend. Send me an email if you need. Good luck with sorting out your project proposals.
Today late my group assignment.
Okay.
Is that okay?
Yeah, you're fine.
Okay, perfect. I just made sure I forgot to go on Tuesday, so I did it.
No, I mostly just don't want it to be very late.
Okay, perfect. Thank you.
See you, Tony.
I didn't recall that too.
Oh, yeah.
Something I forgot.